Hi everyone, I'm Lucas from PUC-Rio, and today I would like to share with you our recent work on the issue of invariance of topological order in the presence of disorder. The idea here is to investigate how different kinds of impurities changes the topological properties of systems that can be described by direct Hamiltonians. And we do that by writing the disordered Hamiltonians in real space, and we calculate the universal topological marker. That's a quantity we can calculate from the eigenstates of the Hamiltonian. This is the outline of this talk. I will start by introducing some basic concepts that are important to keep in mind, and that includes a brief description of this universal topological marker. Then I will show some results we have obtained for 1D and 2D systems. The systems we are interested in are topological insulators and topological superconductors. And what does topological means in this context? To answer that, we can start by looking to this illustration, where we start with some spherical shape and we apply little deformations until at some point we make a hole in the shape, transforming it into a mug. To make a hole, we have to pierce or glue some parts, and that kind of change, we do not call it smooth. The thing is that for each one of those shapes that appear here, we can calculate the integral of the curvature over the surface, and the result will be given by equation 1 here. That's the Gauss-Bonnet theorem. So the result of this integral will be 2 pi times the Euler characteristics. This Euler characteristics is our invariant in this case. And it's a function of a quantity that we call Gines. And in this case, Gines is the number of holes. This means that if we take a three-dimensional shape and apply some smooth deformations, those smooth deformations will not change the number of holes. So they will have the same, so the deformed shape will have the same invariant as the original. And you can say in this case that they are topologically equivalent. So we can make little changes in those shapes that will affect locally the curvature without changing the global parameter that described by the topological invariant. And we can continue to deform the shape until we make another hole at some point. And this new shape will have another topological invariant, because we will have, this new shape, for each hole that we make in the shape, we are changing these Euler characteristics. Those concepts are actually important in physics, because you can use these tools to describe the behavior of some systems, like this classical example of the quantum Hall effect, where the Hall conductance jumps between plateaus as we increase the density, the intensity of the magnetic field. And each one of those jumps are associated with a change in the topological invariant. And depending on the symmetry that the system have, there are different ways to calculating the topological invariant, and that is usually done by an integral over momentum space. There are three important symmetries that we can use to characterize our systems, that are time reversal, particle Hall, and chiral, whose transformations we see here. And depending on each one of those symmetries our systems possesses, we can infer if it's going to have a non-trivial topology, which means a non-zero invariant. And all these can be organized in a periodic table. As I showed before, the invariants are usually calculated from integrals over momentum space. And we do that because the topological properties here are related to the way the ground state vectors in K space are twisted or knotted as we go through the Brillouin zone. If we start to introduce inhomogeneities in our systems, we cannot work in the same way because we are messing with the periodicity. But we still have to find a way of defining topology, even in disordered systems. And one way of doing that is by defining topological markers, which are quantities that we can calculate in real space. And we used here a universal topological marker that's obtained from this universal topological invariant that's defined to characterize the invariant of the systems that can be described by Dirac Hamiltonians. The general form of a Dirac Hamiltonian is in equation 8, where these gamma are Pauli matrices and this vector D contains the momentum dependence of our systems. We can define a unitary vector by normalizing D. And the idea here is to map those states, is to map the states of the torus in the sphere and count how many times it wraps around. This is an integer number, and we call it the degree of the map. We can use this formalism to we can represent all the elements of that periodic table as a function of this universal invariant. So the topological marker we use here is derived from this universal invariant. And I will not delve into details of calculations, but the idea is to write that invariant in real space. And the final form is expressed in equation 12, where ND is a normalization factor. W is given by the Dirac matrices that are omitted in the Hamiltonian. The operators P and Q are calculated from the projectors of empty and filled states that we obtain when we diagonalize the real space Hamiltonian. And our topological order will be given by the trace of this operator. And our marker is given by the diagonal elements of this operator. Once we are defining these quantities in real space, we can calculate them for disordered Hamiltonians. So we can use it as a tool to see what happens with the topological order. And we can do this analytically or numerically. And our analytical work was done by applying perturbation theory. If the element we are changing in the matrix corresponds to a non-zero value, we can, to a non-zero value of the homogeneous Hamiltonian, we can rewrite the new perturbed Hamiltonian as we see here in equation 14, where H0 represents the homogeneous Hamiltonian. And the and the parameter lambda, it's used here to identify the element of the Hamiltonian we are changing. And equation 16 says that the topological order remains the same in the disordered case if the parameter we are changing does not affect the C operator, which corresponds to this derivative here going to 0. And for small perturbations, we can show that this terms goes to 0 in 1D and 2D case. So for a small impurity, we can expect that it does not affect the global order represented by the total marker C, independently of the physical nature that is represented by the parameter we are changing. We also performed some numerical calculations to apply it on some 1 and 2-dimensional system. The first model we studied was the 1-dimensional SSH that we can use to understand what happens that we can use to describe systems like a polyacetylene. The Hamiltonian of the SSH can be expressed in the equation 17, where we have alternating hoppings T plus delta T and T minus delta T, where delta T negative corresponds to the topological phase, and delta T positive corresponds to the trivial phase. Figure A and B here corresponds to the marker pattern as we put two different kinds of impurities in the Hamiltonian. Figure A corresponds to changing locally the value of delta T, which means this is a hopping impurity. We can see that where the impurity changes negatively the value of the marker, there is a positive change near the impurity, conserving the sum of over all sites. This means that the global order remains unchanged. For the case where we add a on-site term, that's in figure B, that corresponds to changing a 0 element of our homogeneous Hamiltonian. The case where we change a 0 element are not covered in that perturbation approach. And we see in figure B that there is no changing around the impurity that will make the sum preserved. And we can say that this case corresponds to a non-conserved case. Another question we can make is what happens when we put many impurities in this system? We can start with one impurity, and we can keep adding more and more impurities until we reach the limit where all the sites are changing. And by putting impurities that overcome delta T, we can turn the system into a trivial phase. And as we approach to this phase, the trace of operator C must go to 0. In those two figures, we can see how we can change the system by transforming it from topological to trivial as we increase the density and the strength of impurities. We can control the gap by changing the parameter delta T here. I'm showing those two figures correspond to delta T equals minus 0.2 and minus 0.4. For delta T equals to minus 0.5, we are deep inside the topological phase, which means the system is more robust to impurities than minus 0.2. And the behavior of the marker allows us to find empirically the conditions under which the topological order is destroyed. we can say that it will happen if we satisfy two conditions. The first is that the average distance between the impurities must be smallest than a correlation length, defined as the Fermi velocity divided by the band gap. And the other condition is that the impurity strength should be higher than the band gap. We can destroy topological order by satisfying those two conditions. Another one-dimensional model we study is the Kitaev chain, where T represents the hopping between sites. Mu is the chemical potential, and we also have this parameter delta here that will induce pairing between nearest sites. We can see what happens when we change locally different parameters, and we can see that in those cases a single impurity does not destroy the topological order. We can also add many impurities like we did with the SSH. I showed in figure B here, where we can see the density and strength we are going to need in order to destroy the topological order. We can also investigate 2D systems like this example of a Chen insulator described by this Hamiltonian. These figures I'm showing here both corresponds to putting single impurity in our 2D Chen Hamiltonian, where the size of the circles in those figures are given by the difference between disordered and homogeneous case for each position xy. And the colors red and blue represents negative and positive values respectively. So in order to the topological order be conserved, the area inside the red circles must be the same as for the blue circles. Figure A corresponds to changing the local potential in just one site, and this corresponds to the conserved case. And in figure B, we introduce in the system a nearest hopping. In that case, the red and blue circles do not cancel each other, which means that the topological order is not conserved here. But to really see what happens in the thermodynamic limit, we must apply finite size scaling. We can also apply this formalism, and we have applied this for the BHZ in the chiral P-wave model. And to investigate finite size effects, we can compute the values of the disordered case and subtract from the homogeneous case and see how this difference behaves as we increase the size of the system. The idea here is that it must converge to zero if it corresponds to the conserved case, and it should converge to a non-zero finite value otherwise. Those figures here exemplifies what happens in those two cases. To summarize what I presented here, we have used the universal topological marker to investigate how the presence of disorder affects the topological order. Our results for 1D and 2D systems show that if we are changing a non-zero element of our Hamiltonian, we can expect the topological order to be conserved for weak impurities and at low density. But as we increase the density of impurities, the average distance between each impurity decreases, and it can become smaller than a given correlation length, where we can destroy the topological order if the strength of impurities are high enough to reach the gap. Which means we can make the system go from a topological to a trivial phase by adding impurities. And if those impurities correspond to changing a zero element of the homogeneous Hamiltonian, we can expect that this will affect the topological order. That's all. I would like to thanks to CAPS and CNPq for supporting us.